So my name is Jürgen Schöftner. I'm a member of the Institute of Technical Mechanics, and my talk today is about refined beam modeling. So first of all, I would like to thank the organizers and also the LIT because they gave me the financial support to do this research and to focus on a topic that attracted me for many, many years, and this is beam modeling. So this is the LIT project. It's a 2-year project, and it is now in its final phase. And it is a follow-up project from a former FWF project, which was about displacement and stress tracking with so-called piezoelectric structures. And so this was a multi-field research, but at the end of this project, it became clear that the literature has some lacks in modeling of thick structures and composite plates, and that was the reason why this topic was created, to focus on accurate formulations for straight beams. And it was just a question of time to combine both goals of this LIT project and this FWF project, and to have an idea for a new FWF project. And this is will start, it actually has started this September, and this is about to get improved tracking methods for refined beam models. So what is a beam? Many constructions only consist of a few recurrent elements, and these are called structural members. And for these structural members, mathematical methods have been developed over the last 100 and 100 years. So the goal of an engineer is to understand and calculate the strength, the rigidity, and also the stability of such structures. If you take a look at this crane, you see that it consists of many, many thin elements, and this is what we call beam element. So if we want to understand the whole construction, we first have to understand what happens with this beam. Further, more advanced elements are plates, and if the plates are curved, then we call them shells. And for example, they occur in this vehicle frame or this aeroplane wing. In this aeroplane wing, for example, these shell elements are used for the surface. Then they are so-called sandwich plates, but you also need some stiffening elements, and these are the spare and the ribs, because with these elements you carry the load of the aeroplane. So here's a short table. What is a bending resistance? Bending resistance means that you can bear tension and compression at the same time. And if you have just something which just has to carry compression, then we call this a column. So as you see it here, there's a certain load, a floor, and the main stress is due to compression here. So here's a comparison of these elements and these load configurations. So a beam is something which deforms under a certain load. But in this case, you don't need a horizontal force to prevent it from collapsing. If you have a beam or a column where the force is in the direction of in the longer direction, then no significant deformation will occur. But you have to take care that this force doesn't exceed the so-called buckling force, because this is a very dangerous situation. This is a typical failure mode in constructions, and there will be a new equilibrium position which will be quite different from this situation. And the last thing is a catenary. A catenary is something so a catenary is the deflection curve of a very, very flexible material. For example, a rope or a cable. And if you don't have such forces, it will simply fall down and collapse. And this is also very interesting from an architectural point of view, because if you invert this curve and you build an arc, you don't have any bending stress. And this is also quite interesting because it can create very huge structures. For example, an example is this gateway arc in St. Louis, and it is about, I think, 200 meters in height. And this is only possible if this shape of this curve has a certain distribution. So here you see this is a composite. A composite is something which is composed of at least two different materials, and it has a certain functionality. One prominent member or example in lightweight engineering is a sandwich structure. Here we have a so-called soft core, and this soft core is surrounded by two very hard phase layers, and these phase layers are responsible for the stiffness of the structure. And the soft core is often realized, or an example is that it has the shape of a honeycomb core. So these are very thin plates whose only task is to keep the phase layers at a certain distance. Another possibility of a composite is a composite laminate, and they consist, they are made of matrix and fibers, and for example the fiber material is in general resin or epoxy or a polymer, and this is a very soft materials. The strength comes from the fibers, and this is for example carbon fiber or glass fiber. And this is also very interesting, for example in sports equipment, because if you stick these layers together and you rotate them against each other, you can increase the strength of such a structure. And here's a very ordinary example, for example a garden hose. So, and this angle, this ply angle of 54 degrees is not an accident. This is the optimal solution for the ply angles if a pipe under a certain inner pressure is considered, because this angle minimizes the deformation. So, and this is a topic that was treated in this project. So I want to show you some modeling strategies. So here we have a cantilever beam, and the goal is to find an expression for the vertical deflection. And maybe you know from elementary courses that there's an elementary theory, and then there exists some more refined theories. These, what I call here fundamental and advanced theories, are so-called assumption-based methods. So this means that we impose restrictions on the displacement field. And this refined theory, what I call here accurate theory or refined theory, this is an outcome from this project, and this is a non-assumption based method. For this theory, I use an energy formulation and a certain mathematical procedure in order to get the higher order beam model. So we have such a simple structure as a cantilever beam. This is clamped at one side, and we have a certain load. And we want to find an expression for an analytical expression for the deflection. So if you have no idea how how to treat something, it's always good to imagine what will happen. And here, the structure will deform. And from this deformation, we can create some approximations or assumptions which will help us to find an analytical model. So one assumption is that we assume that the deflections are small and that the structure is thin. This means that the thickness is very small compared to the length. Then another thing is that if you take a look at this picture, you see that the upper fibers become longer and the lower fibers here, they will be shorter, and there will be a so-called neutral fiber where there's no deformation at all. And also what we can hear from this figure is that there will be an angle which is approximately 90 degrees between the cross-section and this neutral fiber. And finally, we assume that this cross-section remains straight. This just says that distortions of this area will not occur. So, and if you pick out such a small angle and you use these assumptions, you will find out that a rectangle will become a part of a circle. So at the upper side there's tension, on the lower side there's compression, and this situation is called poor bending. And it is also good to think about the properties which will influence the deflection, and of course the load will influence it. And I think this is quite logical. If you double the load, also the deflection will be doubled. And if you double the width or the Young's modulus, the deflections will be lowered. But if you consider the length, there's a nonlinear proportion. So if you increase the length by a factor 2, the deflection will be increased by a factor 16. And similar it is with this thickness of the structure, and this will be lowered. So finally, you find an expression that the deflection will be proportional to the load, to the length to the power of 4, and to the bending stiffness. And if you do a calculation and you compare it to the real solution, this means the solution of a two-dimensional problem, you will find that for very thin beams, this deflection ratio will be close to 1. This means that this formula for this fundamental theory is quite accurate. But if you take a look for thicker beams, there's an error. And this is definitely a problem, because if you go to more thicker beams, you see that this error becomes unacceptable. So we have good results for thin beams, but bad results for thick beams. This means we have to improve our theory. So beside this fundamental term, we need a correction. And this correction will depend on the thickness, as we see in this figure. So maybe our assumptions are too strict. So if you consider this angle of 90 degrees that we had in the assumptions, this is not a very good approximation, because that this angle is not 90 degrees can be explained by the influence of shear, and this is shown here in this figure. If you have a rectangle, it will become a parallelogram after deformation. So for each element here, you have to sum it up, and if you sum it up for the whole of the beam, you get a first correction of this formula. And this is what you get here. This is the blue curve. You also see that for very thick beams, and these are really the ratios how this beam would look like, you see that the error is only 1%. And this theory dates back to Stefan Timoshenko. And this is really, in my opinion, a very good theory also for dynamic problems. And the theory is now approximately 100 years old. So now we could stop here because this is really quite a small error. And how should we improve? So the problem is that we have an assumption-based approach. So this means that we cannot treat topics that are not considered in our assumption. For example, here's a horizontal deflection. In this is a drawing from a finite element simulation, and this middle fiber is not the neutral fiber. So there is due to compression, there's an elongation. And if you combine some really old fashioned methods, like a mathematical procedure for the stress calculation of a rectangular strip and a very old energy formulation, you can get a refined B model. And this is the outcome. This is the red curve, and also for very thick beams, the error is practically not present. And so this seems to be a very good comparison to the two-dimensional solution. And furthermore, if you consider this horizontal deflection, you see that this theory also yields that this middle axis is not the neutral fiber. So this red curve and this gray curve, the gray curve is from the two-dimensional solution, they are practically identical. So, and you can say, do we really need such an accurate theory? So this is just a more practical example. And we also find that this extended method that was created in this project yields the best result. The computational costs are a little bit more, but they are better than the existing theories from the literature. So I have to stop now. But this is not the last slide, but this can be considered as the main conclusions. And thank you.